Alright, love bugs, let's go ahead and look at some electron arrangement notations and some rules that we need to take into consideration when we start looking at trying to write where electrons are. And again, we can't pinpoint it exactly, but these arrangements are going to help us tell us a little bit more about where those electrons are located. Okay, and so some of the rules that we have to consider, first and foremost, is the Aufbau Principle. So this is saying that elements that are in the ground state, remember ground state and excited state, two different things. Ground state, they're filling the lowest energy levels first. Okay, so if you look at orbital notation, I think this is a good visual, trying to imagine that. If you imagine this kind of like a hotel, it's going to require more energy to get up here to these floors than it is this very first floor right here. Okay, so what this rule is saying is it's going to fill these before it fills these. Now, one thing to note, remember this is in ground state. If you see something that is filling higher energy levels before it's filling up these lower ones, that's a hint to you that that's in the that those particular electrons are excited, right? Which is temporary. They will eventually fall back down to ground state and emit those photons that will that we know we can calculate energy for in a different way. But if it's in ground state and they're filling lowest energy levels first, it's always going to feel the same way. We are always going to fill 1s first, then 2s, then 2p, then 3s, and 3p, and you get the idea. Again, I do want to, on the table, remember, these are my s block electrons. These are my d block, my p block, and then my f block. Sorry, I left my expo markers at school. I'm doing this at home. But I know you can visualize S, P, D, and F. And remember, we read the periodic table like a book. Electrons are going to fill exactly like this. Like we read like a book. So first electrons are going to be here. Next are going to be here, which is that 2s, 2p, 3s, 3p, 4s. Remember, in this D block, we're going to subtract 1 from the energy level. So if this is 1, 2, 3, 4, we subtract 1 from that. Then you bump back out to 4p, etc., etc. Okay, so that's where that order is coming from when you look at the table. So you don't have to memorize it. If you can navigate the table, then that's really, really easy. Next, Hund's rule. Hund's rule, this is where, when you use that hotel analogy down here, a lot of people will describe it as you don't want to, if you're in the same orbital right here, so if we were pinpointing the 2p orbital, right, they don't want to doubly occupy orbitals or doubly occupy beds within a room unless they absolutely have to. Okay, so they're going to evenly spread out, and they will not double back up unless they have to. And again, note, if you are singularly occupying them, they are going to have a positive spin first. Now, the next rule is related to that. If they are forced to share an orbital within that same energy level, then they are going to have opposite spins. And this last part, remember that Pauli exclusion is really why no two electrons are going to have the same 4 quantum numbers, because that last quantum number, m sub s, referring to the spins, if they're in the exact same room right within the orbital, one of them will have a positive spin, one of them will have a negative spin. Alright, so now let's actually write some of these notations, because all of these are connected, right? It's just different ways of writing the same thing. Let me find my little pen. Alright, we're going to use red. I'm just using all kinds of little primary colors today. But, orbital notation. So let's just pick one, right? So let's just pick, we'll do one that's short. We'll do sulfur. Okay, so if we're looking at element 19, this is an extra marker. It's alright. RIP, periodic table. Alright, now sulfur. If we look at sulfur, sulfur has, if it is in the ground state, if it's neutral, it's going to have 16 electrons to balance out the 16 protons we see here in the atomic number. Okay, so if I'm looking at orbital notation is a reflection of those electrons as arrows. Okay, so remember that each orbital can only hold 2 electrons. We have 16 total electrons we need to fill. They're going to fill lowest first based on Aufbau Principle. That means my first 2 electrons are going to fill up 1s. Okay? So now, my next electrons are going to go in 2s. Do I have 2 more to give? Yes, because I got to get all the way to 16. So far I've used 4 of the 16. My next ones, we're going to completely fill up that 2p orbital. So notice how I'm writing them, though. You always want to have that positive spin before you go back up and loop them. Okay, so you see how these rules are playing out as we're filling up this this orbital diagram. So now, after 2p, we always go to 3s. So far I've used 2, 4, 6, 8, 10. my next electrons will be here, and we completely fill this orbital. Now, 3p. If we look at where sulfur is on the table, yeah, I might as well keep writing on this. So we look 1, 2, 3, 4, 5, 6, 7. My s orbital, my quantum number, the n is going to be 3, so that's the energy level it's in, and it's located within this p block. So if I'm looking at this notation, I know that my electrons are going to be here. Specifically, I have 1, 2, 3, 4 electrons in that 3p. So if I have 4 more to give out of the 16, I have 1, 2, 3. My last electron, then I can double up as a 4. So let me just double check. 2, 4, 6, 8, 10, 12, 14, 15, 16. There we go. We're done with that. Easy peasy, lemon squeezy. Electron configuration, very similar to orbital notation. The only difference is that we're going to switch out these arrows with exponents. We're going to do it 2 ways. First is the longhand. I know this is kind of obnoxious, right? Which is why I picked sulfur. There's only 16 of them, okay? So that means all of these arrows, we're going to change to exponents. We do not have to write orbital notation to figure out electron configurations. If you know the periodic table and you know where those orbitals are, all you got to do is follow it. And honestly, some of you probably already memorized it because it's just, you know, once you do it one time, you just kind of memorize the order. Okay, but to get to sulfur, we got to go to 1s, and we're going to pass through. And remember, helium comes over to be right here for these purposes. Okay, so we go all the way through 1s2. Okay, so I'm going to reflect that by having this exponent 2 here. Then, after element number 2, we got to go to element 3. So we got to pass in the second energy level, S, we pass through both of these electrons. We're reading the periodic table like a book. After 2s2, after element 4 comes element 5. We are in a different block now, but same energy level. So we got to keep that 2 here. P, we pass all 6 of them. Remember, I got to get all the way down here. So we're going to pass through all 6. So I'll reflect that with my exponents, okay? So now, after this, we're going to come down here to element 11. So now we're in the third energy level. These are in the S block. There are 2 of them. So we'll mark them off. Again, we are finally right here where our electrons, our most external ones, are located. Here we're in the third energy level still, but now we're in the P block. And we are 1, 2, 3. We're in the 4th seat within that 3p. So, as you can see, this is exactly the same as the orbital notation. 1s2, 2s2, 2p6, 3s2, 3p4. So this right here is just a reflection of the spins. It's really the only difference, and it's reflecting them as arrows. If I were to ask you how many valence electrons this particular atom has, remember, valence electrons, the one's furthest away from the nucleus, the outermost energy level. If I'm looking at energy levels here, these are on, if you imagine it like the Bohr model. Okay, we know the Bohr model is inaccurate, but just for this sake, you can imagine these would be in the first ring, second ring, third ring, which means both of these right here are valence electrons. Okay, 2 plus 4, that's 6 valence electrons. If we look at where sulfur is, 16th group, everybody in that 16th group has 6 valence electrons. So this makes sense. Now, if I were to do that same configuration in the shorthand, basically, like, somebody out there figured out that we ain't trying to write this 1s2, 2s2, 2s6 every single time, because we already know if it's in ground state, it's going to feel the same way every single time. So we're going to take a shortcut, okay, shorthand. This is also called noble gas notation. We have to figure out who the nearest noble gas is that we've already passed through, right, on our way to sulfur. So it's got to be the nearest noble gas that has less electrons than the element that we're at. So if we look where the noble gases are, it's got to be one of these right here. So sulfur, 16 electrons. My nearest noble gas is the one before it. In this particular case, it would be neon. So what we're going to do is we're going to put neon in brackets. So basically all we did was we took this part right here and we exchanged it for its symbol in brackets. Okay, we're saying we assume everything up to neon is completely filled. Okay, and then you just write everything that came after. So basically you're writing just the very end of the configuration. Okay, but both of them, again, here, 2, 4, plus 6 is 10, 12, 16, 16 electrons. Neon, we know, has 10 electrons. 10 plus 2 is 12, plus 14, 16. And there you have it.